Anyway, so we'll take a few breaks to reset my camera as we go along here. But anyway, hope you guys all had a good break. I did the Black Friday thing. I've never done that before. I went to Best Buy at 1 o'clock in the morning because I thought that my headphones weren't working anymore. So I'll just go buy some new headphones. I bought the new headphones and I tried them on today and it's not working. So it's the MP3 player. I was like, that's what I should have been getting. But anyway, then I went back out to Black Friday again yesterday afternoon and bought a whole bunch of new shoes. So I'm set. I've never gone through that madness before and probably never again.
Should have done the Cyber Monday.
That's probably the better, yeah. Although with shoes, I don't like to order. I'm very fussy. I have to try them on first. Anyway, been kind of a slow week, but it's going to ramp up in a hurry here. As you know, we have a test in just 4 days. Yeah, so the review packet for the exam is already posted. At the back of the review packet are a few practice problems. So I'd recommend that you try some of those out. And they are somewhat similar to some of the ones we're going to do today here. So it's kind of good that you're here so you can see a few examples and then you can try these on your own. But of course I have the solutions posted as well for all of these. And really if you're looking for practice problems, the sessions 5, 6, and 7 are the one, and today is number 7. Those are the 3 sessions that I think have the relevant material for this midterm. In the review packet, there are a list of the important results that we've covered, mostly on page 2. And there's double asterisks next to the ones that you should be able to prove. Those are the ones that are fairly short or very important, right? There's other things in there that you should know how to state, such as Taylor's theorem, but I won't ask you to prove it. So there's some things you need to know statements of, and then there's some things you should actually also be able to prove. So for example, you should be able to prove that every differentiable function at C is continuous at C. So differentiable implies continuous. You should be able to prove that if a function has a bounded derivative, so it's differentiable on an interval with a bounded derivative, then it's uniformly continuous on that interval. Things like that, where the proofs were fairly short. What I may do is throw a few of them on there and give you a choice. I may not force you into proving any one of them, but if you have a choice, you should be able to pick something that you know how to do from the list. So it's just good to, so part of your studying really should just be reviewing your lecture notes and going back over the proofs and statements of everything that we've done basically since, it's actually not that many weeks, it's since basically the beginning of November, more or less. So it's basically 1 month of material, which is only like, 6 or 7 lectures really. But there are a lot of statements, a lot of definitions and stuff, so make sure you know the statements and the proofs that are italicized with asterisks here. And then beyond that, just practice problems, like the ones we're doing here in the review session. So, anyhow, maybe I have any questions about that? The other thing is there's homework due on Monday, those 5 problems that I put on that handout, and boy, after the problems we're going to do today, that should be really pretty straightforward to finish, I hope. So that'll be good. The problems I'm going to go through today, which are from session number 7, I forgot to print out extra copies, but I'll just write the questions on the board in brief form. They have to do mainly with the last part of chapter 5 and then the stuff we've done from chapter 6. Incidentally, you can kind of think of the material as breaking down into 3 parts. There's the last part of chapter 4, which is about uniform continuity as well as applications of continuity. So things like the intermediate value theorem, the extreme value theorem, just things about uniformly continuous functions, right? They can be extended from an open interval to a closed interval, stuff like that. I'm not going to be reviewing that so much today because that's kind of the earlier part. And then the second section of the material is just chapter 5. So the definition of the derivative. If I want you to prove a derivative from definition, I will say from the definition, but that's really the only way we have of proving derivatives is from the definition or just from our knowledge of the product rule, quotient rule, chain rule, all those kind of things. Okay, so there's really no other way to do it. And then the applications of derivatives is also part of that middle segment of the material. So that's the mean value theorem primarily, and Taylor's theorem. Okay, those are the main ones. And then just things about, you know, monotone increasing and decreasing functions, that sort of thing. So that's all wrapped up in chapter 5. And then the third section of the material would be everything we've done so far in chapter 6. And that will include what we're going to cover on Monday. I'm going to let anything, normally I don't like to, you know, test you on material that I taught you on Monday on a test that we're having 2 days later. So I'm not going to write any questions on the exam that rely on Monday's material, but I will let you be, you don't have to play dumb. Like you don't know it, that we learned it. So if I'm going to teach you, for example, on Monday, that every monotone function is Riemann integrable. So that's something I won't test you explicitly on, but if you happen to know that fact, you can use it. So, but it won't be something you need to know to solve any problem that I ask you. Does that make sense? But anyway, the stuff from basically section 6.1, we've already covered all of that, and so that's the stuff that I want you to be able to do, and you're practicing it in the homework. Hopefully you had a chance to look at my video that I think gives you an overview of how you can work with these problems where you're showing that something's Riemann integrable and evaluating the integral, and we're going to practice that some more today too. So it's kind of those 3 sections if you want to break it down: chapter 4, chapter 5, and chapter 6. Pretty simple. Okay. Any questions before I dive in? Part of the problem with this long break is just getting the wheels turning again. That's part of why I wanted to meet this weekend instead of last weekend, because I thought it'd be good to get the momentum going as we head towards the test. So let's warm up. I'm going to start off in order here at the beginning of the sheet, but I might jump around in a little while. So let's practice. This first problem is not very tightly framed. So this first question I'm going to write down, I probably wouldn't ask it as a midterm question in this form, but I think it's still valuable for us to look at it. It says, use the mean value theorem to find upper and lower bounds for the square root of 105. Okay, so the mean value theorem, I think it was on your quiz, so hopefully you haven't forgotten what it is. Can somebody remind me, what are the ingredients of the mean value theorem? What do we have to have? Okay, we have to have a closed interval, we have to have a continuous function, and differentiable on the open subinterval of the closed interval. So those are all the assumptions, right? So we need a function and a closed interval. Does anybody have a proposal for a function and a closed interval here? Okay, good. So f of x equals the square root of x is a natural choice because we've got that right there. Okay? And then I need a closed interval. Anybody have a proposal for a closed interval? You were here yesterday, weren't you? So you can't answer.
100.
Say again?
100.
Okay.
And 121.
Does that look good? These are easy numbers to evaluate the square root of.
Yeah.
Okay, so what's the mean value theorem tell us? So we've got a closed interval. This is definitely differentiable throughout all of the positive values of x. So that includes this interval. So I think all of our assumptions are good. So what do we conclude?
There's a c in between 100 and 121, such that f prime of c is equal to f of 121 minus f of 100 over 121 minus 100.
Okay. So it's basically the slope of the line that connects the point 10, 100 to 11, 121. Okay. So of course we could simplify this because f of 121 is just 11 and f of 100 is just 10. So 11 minus 10 is 1 over 21. Okay. So there exists some point C in this open interval that has a derivative of 1 over 21. Okay. And of course we know the derivative of the function if we wanted to calculate that. This is just x to the 1/2, and by using the power rule, you can quickly find that the derivative of that is 1/2 x to the minus 1/2, and I'm evaluating that at C. Okay, so that's what we have. Thoughts about where we go from here?
We're gonna solve for C.
Well, I guess we could solve for C, couldn't we? Let's see. C would be, I believe, 21 over 2 squared. If I'm doing the solving correctly in my head. Okay, so that's, actually, this is just, what, 10.5 squared? Makes sense. It's, you know, it's got to be between 10 squared and 11 squared, so that's definitely between. That's 10.5. All right. Trying to find upper and lower bounds for the square root of 105. What did that? So I guess to take it from the silence in the room that we're not sure what to do here. You know, the problem with what's here is that there is no radical 105 anywhere on the board. It's not part of any of these equations. Why is there no radical 105 on the board?
We didn't make it as part of our interval.
We didn't make it as part of our interval, right? So that actually is the fundamental problem here. Everything we've written down is correct, right? But the interval that we chose doesn't have reference to the square root of 105 in it. Matt, would you like to propose a different interval?
Well, I liked our 100, so let's just make it 100 to 105.
Okay, what if we tried this interval instead, right? So same thing, the mean value theorem would give us, there exists a C this time between 100 and 105, such that, well, f prime of C is equal to, this time it'll be the square root of 105 minus 10 all over 5, right? I'm just simplifying it, right? So this time I actually have the square root of 105 sitting in my expression there, okay? And so again, this is 1 over 2 radical C. Okay, but actually figuring out what C isn't really it's not what we need to do. We don't really need to solve for C. That's not the point. We really want to solve for a radical 105, right?
Yeah.
And we can do that now. So the square root of 105, I can solve for that by first multiplying through by 5. So I get 5 over 2 radical C, and then adding 10 to it. I think this is the key equation. And this is where C is between 100 and 105. Agree? So what could we do now to come up with an upper or lower bound on the square root of 105? We now have a formula for it, but it's in terms of some unknown value C. But what could we do now? Remember, we're not trying to find C. We just know it's somewhere in here, right? And so here's the formula for the square root of 105 in terms of this unknown C. So what could I do?
Both sides.
I could pick the sort of the extreme cases for what C is and come up with an estimate, right? So for example, if I put in C equals 100, I'm going to have the smallest possible value of C, which means I'm going to get the biggest possible expression for the right-hand side, which means the square root of 105 has to actually be less than that, right? So in other words, this is less than or equal to what I get by plugging in 100. So putting in the smallest value of C gives me the biggest expression here, and that comes out to, well, square root of 100 is 10, so 5 over 20 is 1/4, so it would be just 10 and 1/4, 10.25. So an upper bound, that's what I wanted, an upper bound for the square root of 105 is 10.25. Does that make sense? Okay, how about to get a lower bound? In other words, I want to go the other way with it. Well, your first thought might be, I'll plug in the other endpoint, but that's that's the unknown that you don't know. That's like giving an upper bound for a value in terms of some value that you don't know. So putting in the square root of 105 for C doesn't really make much sense. But what could we put in that would still give us a lower bound? It might not be as good as we could hope for, but it at least would be a lower bound. Exactly. We could still put in 121, right? We know that that's greater than any value of C in this interval. So I can still put in the square root of 121, right? So this is going to be 10 plus 5 over 22, whatever that is. And this is a pretty tight range of values that radical 105 is sandwiched between. So that's kind of how you do it. This is not a well-framed question. This could not be a test question because it doesn't say how good your upper bound needs to be. I could say, well, the lower bound of 0 and an upper bound of 10 million, and that would be correct, right? Okay, so this is not particularly well-framed, but I did want to point out that sometimes when you're using the mean value theorem, there is some work involved in choosing a function and choosing an interval. And this was the first interval everybody suggested yesterday as well. So at least twice now we've seen examples where people have not quite got the right interval the first time through. So it does take some thought. You could also have used the interval from 105 to 121. That also would have worked. So then you'd get the 121 directly from the interval, and you'd have to go down to 100 to get the other estimate. Okay, any questions about that? So that's the mean value theorem. You need a differentiable function, you need a closed interval, and sometimes choosing those things is the hardest part about it. Okay, let's take a look at problem 2. All right, and problem 2 is show, actually it's got several parts here. For x greater than or equal to 0, show that 1 plus 1/2 x plus 1/8 of x squared is less than or equal to the square root of 1 plus x. Okay, let's try to do that.
Isn't it on the paper you have it as minus 1/8 x?
Oh, minus, I'm sorry. Minus 1/8 x squared. Yep, that's a typo. Thank you. Minus 1/8 x squared. Okay, any idea as to what topic this has to do with? How do you know that this has to do with Taylor's theorem? Yeah, I'm using a polynomial as an estimate for this function, and unless it's a linear polynomial, remember a line really comes from the mean value theorem, but if it's anything of degree 2 or more, it's probably going to be an application of Taylor's theorem rather than the mean value theorem. Okay, so if I'm going to use Taylor's theorem, okay, does anybody remember that theorem? That's got a lot of statements, a lot of pieces to it. You have to have a function. What assumptions does the function have? Well, first of all, you have to choose an order or a degree for your polynomial. So what value of n do you want to use here? You know what I mean? You're approximating a function by a Taylor polynomial of a certain degree. So you have to choose a degree. And you can just see from the left-hand side it's quadratic, so I would expect that n is 2. Right? So if n is 2, then how many times does the function have to be differentiable at the point that we create our Taylor polynomial?
Three times.
3 times, actually, if you remember, because there's a remainder term.
Yeah.
The remainder term is n plus 1 derivatives of the function evaluated at c. Okay, so this Taylor's theorem is something worth putting on a note card. It wasn't part of the review for the last quiz, but the statement of it is pretty long. So the function has to be 3 times differentiable at some point. You choose some point x naught in an interval, right? And by the way, what would be a good interval to work with in this problem? Do we see an interval here? Actually, let me back up. What do you think x naught should be? 0, right? Because let me just remind you that the nth Taylor polynomial is just f of x naught plus f prime of x naught times x minus x naught plus f double prime of x naught over 2 factorial times x minus x naught squared, and so on, right? And because you can see on the left-hand side that there's nothing subtracted from the x, right, that it must be that the x naught is just 0. Okay, so x naught is 0. That makes sense. Okay, this function, by the way, oh, I guess I gave it away. That's the function. I think you would have got that. That function is differentiable as long as x is at least -1. Actually, more than -1. So certainly this is part of that interval, right? So so we have this polynomial, and then the Taylor's theorem says that, okay, f of x is equal to the Taylor polynomial plus this remainder term, and you have to know the formula for the remainder. The remainder is n plus 1 derivatives of f evaluated at c. Where does c live?
In between.
Between x and x naught.
Between x and x naught. In other words, between x and 0.
Yeah.
That should be a hint as to what, we've got to go back to my question, what interval do we want to use? Anyway, so it's this thing divided by n plus 1 factorial x to the n plus 1. Right. Okay, so this is an expression that we never can actually get the exact value for because we don't know what c is. C is just somewhere between x naught and x. And in this case, I know that x is greater than or equal to 0, so I can assume that x is bigger than x naught. Make sense? So my interval, so what is the interval that I'm working with here?
0 to x.
Yeah, 0 to x. That's my interval. Okay. So this is also, everything I've done so far is just basically write down the Taylor theorem in abbreviated form without all the words. Okay, so it looks like what we want to do is we've got our function f of x. We know how to calculate this polynomial. So what we should do is calculate this polynomial, right? And then calculate the remainder, and we will hopefully this polynomial will look something like this, and then we can start to compare with what this equation says. Okay? So let me just take the derivatives of this function. So let's take f prime of x. I'm going to do this really quickly. The derivative is, by the power rule and chain rule combined, 1/2 of 1 plus x to the -1/2, so that ends up on the bottom. And I need to have another derivative of it, so that's going to be, remember this is really 1 plus x to the -1/2, so when I pull that down it would be -1/4, and then 1 plus x to the 3/2 on the bottom. And then I have to go one more time, because I am going to need 3 derivatives of this if n is 2. And the third derivative is going to be 3/8, 1 plus x to the 5/2 on the bottom. Okay, just saving us the time to work that out. Just write all those things down real quick. Okay, so what we have to do is just evaluate, I guess our Taylor polynomial, since n is 2, it stops right here. N is 2. Okay, so let's just start evaluating this. Well, let's basically x naught is 0. So if I put 0 into the original function, here's my original function. If I put in 0, I get square root of 1, which is just 1. Okay, and then I have to put 0 into the derivative, and I'm going to get 1/2. And then that's times x. And then I have to put 0 into the second derivative, and I get negative 1/4. And then that's also divided by 2 factorial here, so it's really negative 1/8 of x squared. Oh, look at that. It's exactly the left-hand side of the inequality that we're being asked to show. Okay, so this is my second order Taylor approximation. And what I would like to know is that my function f of x is actually bigger than that. So that's where we come down to this next line right here, and we say, okay, the second order Taylor polynomial is the left-hand side. Here's the remainder term. The main thing I need to know is that the remainder term is at least 0. Because if the remainder term is at least 0, then I know that the polynomial was smaller than what the function ended up being. Because you added something positive to the polynomial in order to get the function. Does that make sense? So let's look at the remainder term here. The R2 of x. It's the third derivative. I'm just going to evaluate it as c here. Divided by 3 factorial, which is 6, times x to the third. And my question is that positive? Because that's what we want. Is x positive?
Yes.
It's given. If I plug a positive number into the third derivative, so I don't know what c is, but I do know that it's between 0 and x. So if I put a number between 0 and x in right here, and evaluate the third derivative, is that positive? Yep. And 6 is positive, so this is always positive. Actually, it could be, if x is allowed to be 0, so if x was 0, it would be 0. So let's just say greater than or equal to 0. Okay? So the remainder is at least 0. Thus, the square root of 1 plus x, which is my original function, which equals p2 of x, which is 1 plus 1/2 x minus 1/8 x squared, plus r2 of x, is greater than or equal to just the polynomial part alone, because the remainder is positive. So I'm not writing a whole lot of words down here on the board, but you can read my write-up of it if you want to. It's mostly a computational exercise. Does this make some sense? Any questions on that? Okay, if not, there's a part B. Part B says to estimate the square root of 1.3 using part A. So, part B, estimate the square root of 1.3. How are we going to do that? Yeah, the value of x that is relevant right now is 0.3. If I'm looking for the square root of 1.3, then in this function, I want to evaluate f of 0.3. So I'm really asking for f of 0.3. And I'm not looking for an exact answer, because that would require me to take the square root of 1.3. I'm looking for an estimate, so how am I going to estimate it? I mean, the whole idea behind Taylor polynomials is that they approximate the function for you. So you're going to be